what if I told you that one of the most important questions in modern science was solved by 18 scientists who came together to find a solution for an entirely different problem? But to understand why what they solved changes everything, we actually have to start with another unsolved problem that all of us have experienced. Just imagine a time where you're in this flow state, this time of performance where everything is kind of going your way, where the computation is flowing automatically. The actions that you're taking just happen, whether it's playing piano or playing a sport or playing a video game or creative writing or playing music. Whatever it is, there's this time where the actions that you're taking just automatically flow from you without thought, without conscious attention. And then the second, though, that you notice how well it's going, or you start to think, oh, this is the best I've ever performed. If this keeps up, I could break my record. If I keep doing this, this is going to change everything. If I keep doing this, I'm going to reach territory I've never reached before. Kind of like this projection or this measurement or this judgment on how good or bad the performance is going right now. When you have this self-referential processing, it ruins the flow state. It ends the flow state. Right now in cognitive science, we have no real answer tied to neuroscience for why that happens. And it's possible that that might have significant effects on what consciousness is, on what the human experience is of consciousness, and how this could all correlate together when it comes to performance, presence, awareness, the sense of self, meaning, purpose, and what being human really means. All of these are tied together at a really deep level. So fundamentally, we all know that this pattern is universal and fundamental to the human experience. But if that's the case, well, what's causing it? How do you switch from this fast, parallel, seamless mode of being to this slower, muddy, sequential mode of thinking on the other side? And in cognitive science, there's actually already research on this. It's called System 1 and System 2. The question fundamentally, though, is what is this in biology and in neuroscience? Because right now we don't have an answer. But interestingly enough, there's something about this process of observation where we notice how well we're doing, and then it changes what's currently happening. There's a parallel in quantum physics. There's a famous experiment called the double slit experiment. And in physics, particles can exist both as waves and as particles. So when there's two slits in a wall, a wave, as like in water, would go through both slits at the same time, and then they would interfere with each other. The waves would start to interfere with each other and create a pattern. And that pattern can be seen in quantum physics when you're not observing a system, when it's not being looked at, when it's not being measured, that pattern manifests. But then when you look at it, it forces the wave to choose only one of the two paths. It can either go through the left slit or the right slit, and it won't go through both. So this is collapsing the potential. Previously, the wave was searching all possibilities, and then you observe it, and now it's only choosing one, a much narrower landscape that it can manifest. So there's some sort of collapse happening here in your performance and in quantum physics. So could it be possible then that the brain has some sort of quantum hardware that allows for this fast flow state thinking and then slower sequential thinking on the other side? And then could our self-observation be what switches them? Okay, so that's the hypothesis that we're working with here. So then the question is, well, does the brain have quantum hardware? Can quantum processes happen in the brain? And for a long time, this was thought to be impossible. And we'll get into why in a second. And that's going to be directly relevant to the discovery that these scientists found. Given all that, what would actually be required for the brain to run quantum processes? Does it actually have that infrastructure to plausibly exist? And interestingly enough, in biology, we already know that biology and evolution have found ways to harness quantum processes. Photosynthesis is proven to have quantum processes involved in the energy transfer and the efficiency of energy in photosynthesis, and also in migration for birds. There's significant evidence around the idea that they use quantum processes for migration in the electromagnetic fields of the Earth. So we already know, at least in a few domains, that biology has found ways to utilize quantum processes. So could it be possible that the brain, which is the most energy efficient biological invention in the world, could that be using quantum processes? And interestingly enough, in the last really about 4 years or so, 2022, 2023, things have really begun to change, and the evidence has emerged for the plausibility of quantum structures in the brain. And that stems from research in 2023 from Kalra et al., 2024, Babcock et al., Kahn et al. In 2024, a lot of research in anesthesia, Stuart Hameroff and many others, Travis Craddock, and a collaborator of mine, Jack Tazinski, who we'll talk about more later. A lot of their work has become extremely relevant recently in the plausibility of quantum processes in the brain. But the classic counter argument to this is coming from the field of quantum computing, which is the fact that in quantum computing, you have to maintain the coherence of the quantum state. A quantum state can exist between 1 and 0, so it can exist at any degree between 1 and 0, and quantum states are kind of like spheres, so any of these directions can be quantum states. The problem is to maintain the possibility of this entire sphere, you have to have it near absolute zero to maintain coherence for even like puny amounts of time. The classic argument from Tegmark in 2000 was that the brain was too noisy, warm, and wet for quantum processes to maintain long enough to actually do anything in the brain. And that's been the classic argument. It has thousands of citations over the last 25 years. And his paper really shut down a lot of the funding and research for serious quantum biology work in the last 10 to 15, 25 years, really, since 2000. While at the same time, all of the quantum computing research has been heavily funded by major tech and governments because of the use cases that it has. So the economic engine has been funding one side of the debate, but it has not been funding the other because of the economic incentive. The thing here that Tegmark did not consider is that evolution wasn't trying to build a quantum computer. In quantum computation, in computers, the question forever has been, well, how long can we maintain the coherence of the quantum state? Can we maintain it for long enough to run extremely complex algorithms and then have the chance for us to read them and for them to be repeatable over time? That's a much different argument or a much different incentive than what biology has to solve, which is what helps organisms stay alive and survive. They're completely different problems. And so Tegmark was trying to use the constraints of quantum computing to argue why quantum computation can't exist in the brain, and that completely blocked him off from realizing and noticing the completely different system that biology potentially has found to utilize these same advantages, but in a different way. So this is exactly what Nishiyama and all argue in their 2024 papers, that Tegmark completely misidentified this problem and that he treated the brain like a closed system, like what a quantum computer would be. But in reality, the biological systems are all open systems. And this is exactly why these processes could exist in birds and in photosynthesis, for example, because energy pumping comes from an open system. We're receiving the energy from the sun constantly. And considering those constraints, considering the supply dynamics, biology would come up with a completely different type of system for the same process than what humans would do with quantum computers. So this is exactly what Nishiyama and many of these others in the modern quantum biology field have started to point to, is that everyone for 25 years was asking the wrong question, which was originally, how long can a system maintain coherence of the quantum state so that we can compute just like quantum computers? But in reality, there's a much deeper question that needs to be answered, and that is what these 18 scientists accidentally stumbled upon in 2020. Back in 2020, these 18 scientists from like the leading institutions in the world, MIT, the Max Planck Institute, Columbia, Michigan, and so many others, all came together to work on this one paper to solve the one big debate in biology and quantum computation. So this all stemmed from a 2007 paper where Engel et al. Found that inside of photosynthetic proteins, there was 600 plus femtoseconds of coherence of quantum processes. And so this paper was examining that across a bunch of domains in the math and a lot of the research behind it that existed since then, re-examining the quantum biology aspects. And so again, what was this paper exploring? Well, it was exploring how long do quantum processes last? How long does the coherence last, which again goes back to the quantum computation research, that the coherence is all that matters in quantum computers, and therefore it should be the same in biology. So they're still examining the same original question, okay? So what they found was that the actual coherences died in under 60 femtoseconds, which at biological temperature, that's completely wrong. And so not enough time for anything to actually happen, yada, yada, yada. So what did the world do? The science world, the people who did read this paper, and this is where the importance of this paper is completely missed, because what they found seemed to be not that important. See, the original stuff was irrelevant. Haha, boring. And so basically they wrote it off. A lot of people wrote it off as, proof that quantum biology is dead. Or it confirms that biology is too noisy and too wet or whatever for long-term coherence. The coherence is what matters, therefore it's irrelevant. And this was a paper in, a photosynthesis paper. So neuroscience was not reading this. Anatomy was not reading this. Cognitive science was definitely not reading this. Physics wasn't even reading this. It was really just people who are interested in this photosynthesis debate. But this is where the paradox really gets interesting, because what they actually found was, and what they state in the paper is, photosynthesis absolutely uses quantum processes, but it's not because of coherence. So this is why their paper was discounted, because it seemed like the research that they were originally trying to do, which was, is the angle at all paper, is a 600 femtoseconds important, and is it correct? And they said, no, it's incorrect. Therefore, that was the conclusion of the paper. And then everyone ignored the biggest why in quantum biology, or maybe even biology history, if this really does play out. Because think about what they're actually saying here. They're saying quantum processes absolutely exist in photosynthesis, which is like the most important biological process for life on this planet. But they're saying it's not because of coherence. So if photosynthesis is still quantum, but it's not because of coherence, then what is the functional mechanism that's actually taking place here? And that's where nobody read far enough to actually find out in this paper. They just closed off once they got what they were looking for. So now let's read the paper verbatim, what they actually said here. Here's the first part. They say nature does not engineer the bath to avoid decoherence to direct functional processes. Such an approach almost certainly would not be robust. So what they're trying to say here is that trying to preserve the coherence wouldn't work in biology, because biology is an open system. It's very noisy. It's very wet. So Tegmark is technically sort of correct on that front. That Tegmark is if you take Tegmark for trying to say you can't do quantum computing in biology, sure, whatever, okay, great. But what they're saying is that's not what biology is doing. Nature didn't go that route because it physically could not. So therefore, it found another option. So now let's see what it says. Nature, rather than trying to avoid dissipation, specifically exploits it, together with the engineering of site energies and excitonic coupling to direct energy transport. So this is the sentence, and the rest that follows. So nature exploits the dissipation or the decoherence. Biology is not fighting decoherence. Biology is using decoherence by controlling how quantum states interact with the environment at intermediate intervals. And so now let's see what they say next. So in simple words, in a world where the behavior of electrons is governed by the fundamental equations of quantum mechanics and that of the nuclei by classical physics, there would be no preferential downhill energy flow, strongly impairing the macroscopic function of these complexities. So what are they saying here? What they're saying here is that if you tried to model this like a classical system that did not have quantum, the energy flow wouldn't happen. It would break. The system would not work. And so what they're saying is the nature of quantum mechanics, of how things lose coherence. So the nature of decoherence itself is what creates the function in biology. So they're saying evolution harnessed decoherence to create efficient computation and energy transfer. Then they say in the next sentence, the basic physics behind thermalization is used to impose direction in the system. So losing coherence to the environment is what creates the direction of the energy transfer. So the collapse itself is literally part of the mechanism. That is insane. And so Then they say this simple concept, mastered by nature over all relevant time and spatial dimensions, is truly a marvel of biology. So they're literally saying that over all relevant time and spatial dimensions, there's this general, this is the general biological principle. It's like, this is a paradigm shift that I'm not even sure the authors fully recognized when they wrote this, because like we said, the entire field had been asking, well, how long can coherence be maintained so that these processes can exist in biology? But what their own paper is showing here is that was not the right question. The right question is there sufficient energy throughout the system to sustain continuous cycles of quantum processing and controlled decoherence at functionally relevant rates and timescales? It's a technical sentence, and I had to write it down to make sure it was correct, but that is the fundamental question that has to be asked in biology. Because again, biology is a fundamentally open system. Our bodies are intaking photons from the sun constantly. We're intaking food, we're converting it into energy. And so somehow this metabolic process is happening that creates energy in our body and then disperses it to everywhere it needs to be. This paper is literally showing that biology's trick for quantum processes in biology is to engineer decoherence in an open energy pumping system, which then completely obliterates the too warm and too wet objection, because it's happening in biological systems already at quantum relevant scales. So this paper is saying that biology never needed to maintain coherence to utilize quantum processes as long as it has the energy that it needs to sustain it for a long enough period for the computation to take place. So then all you have to ask then is, can the brain supply energy to the quantum structures in the cells to maintain coherence long enough to convert those computations into something useful? And that is where the huge breakthroughs happened in the last 2 to 3 years in quantum biology research. Nishiyama et al. 2024, they have multiple papers that year. And then Kurian 2025, and he has multiple papers as well in the past few years. Cavaglia et al. 2023 with Jack Tazinski also have papers that all discuss the math and the biological evidence behind the fact that microtubules and other relevant systems in the cytoskeleton can receive energy pumping from action potentials, for example, at rates that would allow them to maintain coherence for enough time to make computations and be relevant to the entire biological system. And so these processes fundamentally exist based off of the exact evolutionary trick that was found in the 2020 paper from Chow et al. So that's what's important to consider here, is that the brain doesn't need coherence to last for one really, really long amount of time. All it needs to do is cycle through very, very short ones over and over and over very quickly, exactly like photosynthesis already does. So considering all of that, back to our original observation, which was the fact that our self-observation can collapse these fast-thinking states into slow-thinking states. This now would make a lot of sense in a quantum regime in the brain. The fast side would be quantum infused with more coherence, more quantum processing going on, pattern recognition, prediction, and this felt sense of presence and connection to the world would make a lot of sense in this fast regime. And then the slow regime would be the classical behaviors, the classical neuroscience, the linear thinking, the language, all of these things that have built society would be on this side. So then the question is, what is the switch? How do you collapse the quantum states, ruin the coherence, prevent quantum computation, and where's the benefit of being in the in-between? Well, clearly both have their advantages for survival. You need to be able to follow the patterns and be able to predict where something's going to be and notice patterns immediately and quickly and have instincts in that sense. But at the same time, you need to be able to think logically, communicate with your tribe, plan, to strategize, to think into the future. So you have both that have to play out. You need to have the instincts and then be able to translate the instincts into survival in the long run. Then the question becomes, well, then how do you switch between them? And we already have a hypothesis for the switch. The switch would then have something to do with our self-observation, our our internal thinking, our sense of self, our sense of how this affects me, what the meaning of this moment is. And neuroscience already knows what that is. That's the default mode network. That's the ego. That is the sense of self, the sense of narrative, the sense of self-purpose, the long-term coherence of who I am as a person, what this means for me, hot and cold, this and that, me and you, here and there. It's a differentiation engine. In quantum states, there would be a handful of things then, based off of this logic, that would help the regime switch from this fast thinking to the slow thinking. Well, the first one would clearly be what they found in photosynthesis, which is the energy. The energy itself needs to be at a certain level to enable the energy pumping to allow for these quantum states to take place very quickly. And we already know this exists in the brain. And interestingly enough, in correlation to the default mode network, the default mode network actually uses 40% energy above baseline. Carhart-Harris research shows this. When you silence the default mode network, whether through meditation or through presence or through a lack of self-referential thinking in general, that's freeing up energy to go elsewhere in the brain. And where would it go? Well, maybe it goes to energy pumping in microtubules and allowing for additional coherence or more coherence across the brain. Another thing that the default mode network does is electromagnetic interference. And this is well known, well established that there is a ton of electromagnetic interference with the default mode network itself. I mean, Panatsis et al. In 2023 proved that these fields causally interact with microtubules themselves. And Weiss 2025 identified the calcium pathways, which microtubules feel the neural activity of the brain and electromagnetic fields. So we know that there's already communication going on here at this level. So in quantum states, we know that you have to preserve quantum states by protecting them from noise. Well, if the brain is, there's a ton of electromagnetic noise from the default mode network when it's processing all this about yourself, well, then clearly there's going to be more interference with the quantum states and there's going to be less coherence across the board in the brain. So there would be clearly a correlation between self-referential thinking and the lack of flow states. That would be a fundamental prediction of our initial hypothesis based off of what the Chow et al. 2020 paper found. And then not only that, but then you have to have the structural environment, the underlying microtubules have to be structurally sound for the quantum coherence to take place. And interestingly enough, what we find is that when you inject certain chemicals into the brain or into microtubules, for example, like anesthesia and a variety of other compounds, it actually weakens the microtubules themselves, and that can ruin the quantum processes as well. So we need the underlying structure, and the evidence already exists for that. And then not only that, there's also a geometric constraint on what could get computed. And so inherently, you have to ask, well, what are beliefs? What are worldviews? What is the default mode network doing? Well, it's creating structure. It's creating meaning. It's creating beliefs about how the world works, how things are. And what are those things? What are beliefs? Well, at some level, they have to be there has to be correlated to energy in some way because it's existing in your brain, in your head. And so they have to be some sort of energetic system that's engraved or maintained into your neurobiological system in some sense, whether it's hypothesized how this may work. I mean, Cavaglia et al. Hypothesized that it's through holographic principles that actually encode the memory into the membrane itself. And so that's a plausible hypothesis, as well as classical memory hypotheses that exist out there. But anyway, all of these constraints constrain what can be computed. So actually, when the default mode network is active, it is compressing what can even manifest from the computation itself, which itself could be ruining the flow state. So there's a lot of correlation here between the default mode network and the experience of flow, the experience of presence, and the experience of your performance that manifests. And there's a reason why self-referential thinking and performance then would be highly anti-correlated, because you need to have less self-referential thinking for performance to increase in flow states. So all of those four move together as variables that shift what can manifest for humans in the brain, all coming from the one Chow et al. Paper and the modern research that has emerged in quantum biology in just the last 2 or 3 years. I mean, fundamentally, if this is even sort of true, then this has massive implications on humanity across the board. Psychology, obviously, but when it comes to science, physics, I mean, the underlying physics of this also are extremely important, and that's what the book goes on to explore. Me and Jack Kaczynski wrote an entire book on this and multiple papers along these fronts, and those will be linked down in the description below as well. But these are the hypotheses that drastically affect human consciousness, human psychology, performance, education, sports, a social identity, the self, beliefs themselves, meaning, purpose, how we interact with each other, the world, and how we interact with our own thoughts and our own sense of self. And these are long-term implications. And a lot of these things are things that contemplative traditions have been considering a long time. This idea of letting go of the self, dissolving identity, dissolving beliefs, being quiet and finding the wisdom in the stillness. And, examples across all the board here are very relevant when it comes to what this may mean for the universe and for all of us individually. And it creates a really interesting dynamic for where research could go from here in science, psychology, cognitive science, quantum biology, physics, and really, everywhere else across the board, really. So hopefully this gets you thinking, gets you interested in what may be about human consciousness, about the human brain, about quantum physics, and everything else in between. And hopefully you guys have fun hanging out with me while we all talked about this. So talk to you very soon. Peace.